In this temperature control lab exercise, we're going to use block diagrams to be able to compute the analytic solution to closed loop behavior. So if we have a loop with a PI controller, we are going to calculate what is the response with our process model here. What is the response of the output temperature to an input set point change? And we'll have a closed loop system like this. We'll also have a disturbance and add in the disturbance, compute what is the effect of our second temperature on the output response, given that we have a closed loop system with a PI controller. So let's get into the details. It's a little bit heavy on the math, so I want to go through each of the steps. If you'd like to follow along with the source code, you can do that here. It will bring up a web page that will show you the material that we're going to go through here. Alright, so the overall objective is to determine the closed loop response of a PI controller to a step change in set point, and we'll compare the analytical solution to the closed loop response with the data. We have a little bit of information about each of our blocks in this system. We're going to use this for our controller, this transfer function for our process, and this transfer function for our disturbance. Now if you recall, we got these by taking the differential equation or the PI controller equation and doing a Laplace transform on each term. And then this is a transfer function that relates the input to the output. So if you need help with that, I'd recommend this link here for the PI controller, and then look at the prior one on Laplace transforms if you need help on this one. Okay, so here is our block diagram with our different transfer functions that we have here. This PI controller right here is going to be Kc times tau is plus 1 divided by tau is. Okay, so we're going to put that there. Alright, so we have all the information we need. One of the shortcut ways to get a closed loop transfer function in a standard feedback control system is that the closed loop is going to be equal to direct divided by 1 plus the loop. Alright, so that means if I want to get a transfer function, T1 of S over T2 of S, our disturbance right up here, then I can just do whatever transfer functions are direct between those two. And so that's just going to be GD, and then I'll say this is GP, and then this is GC down here. Okay, for our process, disturbance, and controller. So if I want to get that, then I have GD, that is direct between the two, and then divided by 1 plus the loop, which is just going to be GC times GP. Alright, there's my transfer function that relates an input disturbance, maybe that's a step. In this case, if I do 20 divided by S, that equals a step of plus 20, and then I can compute what is the T1 value that results from that. Alright, let's just look at the block diagram algebra. We can get this same thing right here, but in a more general way, just by looking at the algebra of the system. We have our error, which is just going to be the set point minus the T1 value right here. We have a plus minus right here, and our error is just going to be the difference between those two. We have our Q1 value right here, which is just going to be our controller times the error. Or if I plug in the error right here, then I get controller times T set point minus T1. Alright, and the parentheses here, S, that just indicates that T1 is a function of a Laplace variable. It's a signal that's in the Laplace domain. Alright, if I continue on down, I have TA1, and I'm just going to label this T TA1 right here, and then this is TB1. Okay, those are the two elements that make up T1, and so that's just going to be GP times Q1. Okay, so I take Q1, I multiply it by GP, and then I get TA1. And the same thing with TB1, I just take GD, and I multiply it, T2 times GD to get TB1. And then this T1 is just going to be the addition of the TA1 and the TB1. And so I just write that here and then substitute in the two that I computed. Okay, this is all just algebra. I'm going to plug that one in here, and this one goes in right there. So now I have this system, this equation right here. And if I say that the set point is not going to change, then this term goes to 0, and I'm left with this expression that's just a function of the two signals that I'm interested in, T1 and T2, and my transfer functions. And then if I move this term to the left side and then factor out T1 of S, and then divide through, then I get something that looks like my direct divided by 1 plus the loop, and then I can plug these in. This is actually going to be GC here instead of KC. Alright, there is my transfer function. Now the one thing that I've got to realize is I can't take, if T2, if that's going to be equal to 20 divided by S, I'll multiply that over. I've got a problem here because I can't do an inverse Laplace transform on these e to the minus 15s if I don't have something here as well. So I need to make an approximation to that. There's a couple different ways that you could approximate these to get that back to polynomial form so we can get our analytical solution. One is a pod A approximation, and this has a number of additional terms that continue on. You can look at the article on that for pod A approximation for the exponential function. Sometimes we just choose the first two terms, and if we do that, we take our 15 and then divide it by 2 and to get this expression for an approximation. So we could use that one, or we could use a Taylor series approximation as well. Taylor series approximation for the exponential function is this infinite sum right here, and we just take the first two terms similar to what we did in linearization. So we just ignore these. It's not going to be a very good approximation, but it'll be good enough for our application. Alright, so I'm going to take my exponential term. I have 15 seconds of time delay, and I'm just going to put that into the denominator. The negative goes away, and then I'll do the Taylor series approximation just for this, which equals 1 plus 15 times s, or this in time constant form. So I'm basically just adding a lag there of 15 seconds to approximate the delay of 15 seconds. So let's go on with that approximation and get our analytical solution to the PI controller response to a 20-degree disturbance change in T2. So here is T2 up top, and this is our predicted T1 as a function of time. And the way we did that way, we came up with this analytical solution to T1 is to use the inverse Laplace transform, be able to convert it back into the time domain. So let me just show you how to do that with SymPy in Python. I'm just going to import some symbols here, S and T. I import the inverse Laplace transform from SymPy integrals, and then I set up my transfer function. So I'm going to put in my KC value of 2, my tau I of 180 seconds. Here is my PI controller and my delay approximation, and then my two transfer functions that I have, my disturbance and my process. And then here is my closed loop response. GC is just going to be direct divided by 1 plus the loop. And then I know that my T2, I'm going to start that, I'll start that at 1 second, and it's going to be plus 20 on the step. Alright, now I want to do an inverse Laplace transform, and then it's just plotting the values. Alright, so I need to substitute the symbolic expression for t with specific times that I want to see the solution at. And I'm not going to put these 23s in here because I'm just going to do temperature change and then plot it like this. Alright, and this is going to be the solution right here. So this is all just an example to show you how to do this same thing, but now instead of the disturbance, we're going to do it for the set point change instead. So I'm going to go back up just to the block diagram, and now instead of being concerned about the disturbance, we're going to do the closed loop response with direct divided by 1 plus the loop, but for our set point changes. So here we have our set point change here on the left, and we want to compute the transfer function, which is T1. How is T1 going to change for T set point? So instead of our disturbance, T2, we're going to compute what is the expected response for a PI controller when I have a set point change. I'm going to go up by plus 20 again. I'll start at 23 degrees C and go up to 43 degrees C. And what is going to be that response? We can compute that analytically. So just like we had before with the direct divided by 1 plus a loop, if we use a set point here instead, okay, the direct is going to be our controller and our process. So instead of GD at in the numerator up here, we're going to use the controller and the process and then compute the analytical solution. So let me go in and I'm going to go ahead and just we already walked through some of this building the script, and then I'm just going to modify it so that we can compute the closed loop response to a set point change instead. Alright, so here is the script and the plot. Alright, and what I'm going to do here is just modify it. It'll be in the solutions as well, but I'm just going to say this is going to be a set point. I'm just going to leave it as T2 for now, and then alright, down here instead of GD, I'm going to have GC times GP. Okay, that's really the only modification that you need to make, or you could go in and rename all your T2s to something else. Alright, let's go ahead and run this one and just see what our expected response is to a 20-degree set point change. Alright, so there I have the set point change from 23 to 43, and we just get rid of the T1 set point. Before it was the temperature change, and so if there's a disturbance we want to just keep it at the set point. But here you can see the response. Alright, the other thing I'm going to do is take this analytic solution that it came up with and then add it to the PI controller test. Now this was in okay, this PI controller test was in the bottom. There's a script for it. I'm gonna have 20 plus. Okay, here we go. 20 plus, and then the first part, the second part, and the third part. Okay, so here's our analytical solution right here. And what I want to do is now run this PI control test so that it comes up with the measured values, but also the analytic solution to it as well. and then it will compare them in this plot. So the only thing you need to modify from this script, this PI test, that's given, I'll show you where it is at the very bottom. Alright, if I go to schedule, we are on number 17, which is block diagram. And if you go down, okay, the PI test script is right here, and you just need to fill in the analytical solution into the test script. Okay, so we're going to fill it in right here. Don't forget, if you're going to download this script, just use the get code link to get it for you in raw format. Alright, let's go ahead and run this and just see how it does. And I just realized when I was doing the code explanation on this disturbance, I think I had it on my other screen. So I apologize for that. You know, here is the GC times GP. That was the one thing that we needed to modify, and then we could run it again. We did rename this for closed loop GC, so it overwrites this GC value right here. Okay, but it should give you the closed loop response there, and what we're going to do is just compare the measured values to this one. All right, let's go in on the PI script test and just run this. You should be able to connect your Arduino device. You can run this through Jupyter Notebook. It's just going to have some of the values printed out, and here it goes. Okay, so we have the heater value, the temperature, and the set point, and this is going to run for 10 minutes, and at the very end it should show you the analytical solution and the measured values together. So we're trying to see if our analytical solution is correct. Okay, it looks like it's almost done running. It's almost to the set point. Again, the thing that we had predicted was right here. I'll go ahead and just run this one again just so we can see it. This is going to be our change from 23 degrees up to 43. As you can see, it's just it's past this time where it's getting right up to the set point, and we'll see the measured values as they trend right along here, hopefully fairly close to the analytic solution. Alright, so let me just go ahead and minimize this. You can see again the heater, the temperature is getting very close to 43 degrees. Because we have that integral term, it reduces and eliminates the offset, but this isn't a very well-tuned controller. You could in fact get a better response if you increase the controller gain or reduce the controller time constant. So we'll just give this just a little bit more to finish. Alright, it just finished. You can see the temperature that started off at was just a little bit lower. So if we had had it in an ambient temperature of 23 degrees, it would have been closer. But you can see here the predicted is the blue, and then the measured is the red. You can see a fairly good agreement here between the two. Now, one of the weaknesses of this analytic solution is it doesn't consider controller saturation. So if the heater had gone to 100%, maybe the analytic solution would have predicted that it would have gone above 100%. So sometimes you get slightly different answers if you change the tuning values, and it's an aggressive enough controller that it wants to saturate the controller output. But fairly good agreement there. I ran it another time as well. I'll just show you that solution here in the at the very end. So here's another time that I had run it. Again, fairly close between the analytic solution and the predicted and the measured values there. Okay, so the predicted is the analytical solution. All right, that's it. We've used a block diagram to help us compute what the expected closed loop response is going to be, both to a disturbance but also to a set point change for a PI controller. And let me just come back up here to the overview of the course and where where we are on this map. So we are modeling the controller performance. We're modeling an analytical solution to tell us, as I change Kc and tau I, how that affects controller performance. And I'm doing that with Laplace transforms and transfer functions. Okay, the same ones that I'd used up here to model our system. We're also using those same ones to come up with a closed loop response. So to come up with an analytical solution to our closed loop response between a set point change or disturbance change.